All right, ladies and gentlemen, welcome back to another video with Mr. Kenton for HL Chemistry. We're continuing our discussion on atomic structure, and we're moving into mass spectroscopy and mass spectrometers, which are a pretty useful tool for a chemist because it allows them to determine the different types of isotopes that exist for different atoms. So I know in our previous classes we've talked about how there are these different isotopes for each of the atoms, that there might be 2 isotopes, there might be 5 isotopes, there might be 7 isotopes. And the question might be, well, how do we know that there are those different types of isotopes? And so it boils down to chemists' ability to use what's called a mass spectrometer. And so a mass spectrometer is something that's used to determine the relative atomic mass of an element from its isotopic composition, right? And so you think about all the average atomic masses that are on the periodic table. Those have been experimentally determined using a mass spectrometer by looking at that isotopic composition of the element. So let's just kind of dive into it. What exactly is a mass spectrometer? What does it do? And how does it help us understand this? So the mass spectrometer, what it is, it's used to measure the masses of different isotopes and their relative abundance. So like how often it can be found in nature, right? And so certainly different isotopes of different elements occur more frequently or less frequently compared to each other, right? That's why when you start looking at the masses on the periodic table, you can take a good guess as to what isotope is probably the most common just based on its average atomic mass, but that's not always the case. So it's something that helps us understand the relative abundances of the isotopes and how that contributes to the overall or to the average atomic mass of the element as a whole. Now, our mass spectrometer has essentially 5 basic operations that it's going to perform during this process as we're determining the relative abundance and the masses of the isotopes. So in order to kind of see that, let's just take a look at a diagram of what a mass spectrometer looks like. And this should look very familiar to you guys. Pretty sure that there was an image very similar to this in the POGIL activity that I had you guys do. And so when you look at it, you're going to start on the left, right? And so what you're first going to do is you're going to vaporize your sample. So whatever it is that you're dealing with, you're going to convert it to the gas phase, right? So once you do that, it's going to hit the ionization chamber. And so what the ionization chamber is going to do is it's going to provide enough energy to start removing electrons from its valence shell. So you're going to be forming a positively charged ion. Now, once it's ionized, it's going to start to move and it's going to pass through this area of acceleration. So it's going to start to speed up the particles as they're moving, right? And so now you've got these gaseous ions that are moving through your mass spectrometer. Now, as they're moving, they're going to come in contact with an electromagnet. Now, the purpose of the electromagnet is going to be to cause those ions, those gaseous ions, to deflect. Now, what you see, there are 3 different paths that you're seeing here. You've got the blue path, you've got the red path, and you've got the green path, right? And so the deflection, the degree to which it's being deflected, is telling us something about the mass of that particular particle, right? So the one that's been deflected the most, the blue one, that's going to be our lightest particle because it's being impacted by the magnet the most. Green is somewhere in the middle, and red is probably going to be our heaviest isotope because it's not being deflected as much as it's traveling. Now, as it's moving, notice that you have the vacuum pump. The purpose of the vacuum pump is to remove any of the sample that remained gaseous but was not ionized so that it doesn't impact the data that you're recording. So the vacuum pump removes those gas particles. And then your particles are moving. They get to the detection site. And then once it passes through the detection site, what's going to happen is the mass spectrometer is going to produce a graph, a readout, that's going to essentially give you the mass to charge ratio of how often you're seeing each individual isotope, right? So that's essentially how the mass spectrometer works. Now, what kind of information does it give you once it's been completed? Well, it's going to look something like what we see here in this image on this slide. You've got this M over Z, that's going to be the mass to charge ratio, and for the most part, when you're looking at mass to charge ratio, it's always going to be the mass of the substance with relation to a charge of +1. So it's always going to be the mass divided by 1, right? And so the results of the mass spectrometer are presented in the form of a mass spectrum. So the x-axis has our mass to charge ratio, the y-axis has our relative abundance. And so based on this particular mass spectra, what we're seeing is, at least for molybdenum, the isotope that occurred the most was the isotope that had a mass of 98, right? It has the highest peak. Now, based on this, if we look at the mass spectra data, what we can determine is, all right, there are 1, 2, 3, 4, 5, 6, 7 different isotopes of molybdenum. And then we can use the relative abundances to figure out what the actual or what the average atomic mass is for molybdenum as a whole. Now, let's talk about the relative atomic mass. So relative atomic mass, A sub r, of an element is the average mass of an atom of the element, taking into account all its isotopes and their relative abundances. So based on that definition, that's going to sound a lot like our average atomic mass, which is found on the periodic table. So those terms can be interchangeable. And so if we consider that, this is why the atomic mass of an element is not a whole number, because you've got these differing isotopes with their different abundances, which are going to cause the mass to be changed. And so it's not going to fall into a nice, neat whole number. Now, it's important to recognize that every single one of those isotopes does have a mass number that is a whole number, right? But when you start combining all of those pieces, you end up with a relative atomic mass that's not a whole number. So just something to consider as you're moving forward, right? Now, looking at mass spectrometry, what you should be able to do is to be able to calculate a non-integer relative atomic mass and abundance of isotopes when you've been given data, including mass spec data. Okay, and so let's take a look at some examples of what that would look like. So what we know is the masses of atoms of all elements actually range from 1 times 10 to the negative 24th to 1 times 10 to the negative 22nd grams. Again, that's a really, really small number, right? Like, we're in the magnitude here of Avogadro's number, but in the opposite direction of how small it is. And so for us, from a human perspective, it's hard to put that into context. And so what chemists had to do is they said, all right, these small numbers, hard for us to kind of grapple with and work with. So we need to come up with relative values that allow us to understand this from to get a deeper understanding from a perspective that we can kind of wrap our minds around. So to use the relative values, chemists, scientists had to come up with a standard to agree upon, right? So that scientists who are working in the United States, scientists who are working in Europe, scientists who are working in Asia and India and Russia and all these different places, so they could be able to communicate clearly and consistently across the board. So they had to come up with a standard. And so the standard that they chose was the carbon-12 isotope. This was chosen in 1961. And they said, all right, carbon-12 is going to have a relative mass that we're going to say is exactly 12.000. Okay. And so in doing that, that helps set up the ability to communicate about the masses of every other element on the periodic table. Right? So when you think about it, when you look at your periodic table, everything is being measured with respect to carbon-12, which is kind of interesting when you think about it. Now, here's an example of a type of problem that you could be asked to do. Right? What is the relative atomic mass of chlorine if it has 2 isotopes with the following abundances? So they tell you chlorine 35 at 75% and chlorine 37 at 25%. This is by far the easiest problem they could give you because they've essentially told you the masses and the abundances of each. And so when we go to solve that, we're just going to multiply the isotopic mass by the abundance and then add the two values together. So you got 35 times 0.75 plus 37 times 0.25, and we get 35.5 AMU, which if you look at your periodic table, chlorine, if you look at it just the three significant digits, would be 35.5. Right? So that's kind of the first way. It's also probably the simplest way. All right. The second example is going to be if they tell you, all right, boron exists in two isotopic forms, boron 10 and boron 11, and they say use your periodic table to find the abundances of the two isotopes. All right. So they've told you what two isotopes you have, but they haven't told you which one is more abundant. So what you're going to do in this situation is, you're going to look at the atomic mass of boron that's indicated on the periodic table. So we see that boron is 10.81 is its average atomic mass. Now, if there are two isotopes, what that means is that there's going to be more boron 11 than boron 10, right? Because it's 10.81, that's much closer to 11 than it is to 10. So as we look at that, what we're going to do is we go to set this up. We're going to say, all right, let X atoms be boron 10. Therefore, boron 11 would be 1 minus X. So when you think about this, we have to multiply the isotopic mass by the abundance to get the total mass. So essentially what we've done is we've created an algebra problem. We know it's 10X plus 11 times 1 minus X equals 10.81. Well, you go through and solve it. You got 10x plus 11 minus 11x equals 10.81. You got 11 minus x equals 10.81. 11 minus 10.81 equals x. X is 0.19. So the abundances for boron 10 would be 19%, and then boron 11 is at 81%. Right? Now, again, I think the walkthrough of that's pretty straightforward, but just kind of take a look back at that. If you need to rewatch that, look at it again, feel free to do so. All right. Now, the third type of way that they can ask you to determine the average atomic mass of something is looking at mass spec data, like what we've been given right here. So you've got this particular isotope. This looks like this is, again, probably boron again, at least at 10.19. That's probably the closest thing that we've got. So you've got an isotope that's at 10, and then you've got one that's at 11. They've given you the percentage abundances, and then you can just simply multiply the numbers together. All right. Now, the last thing we're going to take a look at is comparing the properties of an isotope, of isotopes of elements, right? And so when we talk about isotopes, we know that the only thing that's different is the number of neutrons. And so different isotopes, whether we're talking about carbon-12 or carbon-14, they're going to have the same chemical properties as their parent element, since neutrons do not affect how an element chemically combines with other elements. So that's kind of an interesting thing to consider, right? So different numbers of neutrons, different isotopes actually have the same chemical behavior as their parent element. Now, what we do find is that isotopes that have more neutrons are heavier and move more slowly at a given temperature. And so certainly one thing that you can do, because it's heavier, you can use this as a means to separate the different isotopes if you need to. But again, from a chemical perspective, different isotopes behave the same chemically because the number of valence electrons has not changed. Okay, another thing to consider is that as you start to change the number of neutrons, it does affect physical properties like boiling and melting point, mass, density, and rate of diffusion for gases. Because again, if you're adding more mass to the substance, you're creating possibly instances where intermolecular forces can be changed and things like that. So differences in neutrons can impact physical properties, but it doesn't impact chemical properties. Right? And just as a reminder, physical properties are something that can be measured without changing the chemical composition of the substance itself. All right, and ladies and gentlemen, that's it for this first section. I know that should have been just a huge review. Probably the biggest new thing, or maybe the thing that you needed brushed up on the most, would have been with mass spectroscopy. So thank you guys for taking the time to watch these videos. If you do have any questions, please don't hesitate to ask in class, and I look forward to seeing you guys again real soon. Take care.